Picture this, a single cluster of stars, so densely packed that if you were to stand on a planet within it, the night sky would never truly be dark. Instead, it would glow with the light of hundreds of thousands of stars, each one a blazing beacon in an endless cosmic dance. This isn't science fiction, it's the reality of globular clusters, some of the most ancient and mysterious structures in the universe. These celestial wonders are like time capsules, holding secrets from the dawn of creation, and yet they continue to baffle scientists with their strange and unexpected behaviors. Today, we're diving into 25 of the most mind-blowing discoveries about globular clusters, discoveries that challenge what we thought we knew about the cosmos and leave us with more questions than answers. From rogue planets wandering freely to stars that defy the laws of aging, these clusters are a treasure trove of cosmic mysteries. So, buckle up, because by the end of this journey, you'll see the universe in a whole new light. Let's begin. Now, let's step back in time, way back. Globular clusters are not just dense collections of stars, they are ancient relics of the universe itself. These clusters are among the oldest structures we know, with some dating back nearly as far as the Big Bang. Imagine that these clusters have been around for over 13 billion years, witnessing the birth and evolution of galaxies, the formation of stars, and the rise of cosmic structures. They are like living fossils, preserving the conditions of the early universe in their tightly bound stellar communities. What makes them so significant? Well, globular clusters offer us a rare glimpse into the universe's infancy. By studying their stars, scientists can piece together the chemical composition and physical conditions of the cosmos shortly after the Big Bang. These clusters are like cosmic time capsules, holding clues about how the first stars and galaxies formed. And here's the kicker: despite their age, they've managed to survive for billions of years, enduring the chaotic forces of the universe. Their resilience is a testament to the incredible gravitational bonds that hold them together, even as they orbit through the turbulent environments of their host galaxies. So, when we look at a globular cluster, we're not just seeing a beautiful collection of stars, we're looking at a piece of the universe's history, a snapshot of a time when everything was just beginning. And that's what makes them so extraordinary. They remind us that the universe is not just vast and mysterious, but also incredibly ancient, with stories written in the stars that have been shining since the dawn of time. Now, let's zoom in a little closer, because the density of stars in globular clusters is nothing short of mind-blowing. Picture this: if you were standing on a planet inside one of these clusters, the night sky wouldn't just be dotted with stars, it would be ablaze with them. Stars in globular clusters are packed so tightly together that, from within, the sky would be a dazzling sea of light, with stars appearing almost shoulder to shoulder. In fact, the average distance between stars in a globular cluster can be as little as 1 light year, compared to the 4 light years between our Sun and its nearest neighbor, Proxima Centauri. That's like comparing a crowded concert to a quiet park bench. To put it another way, if you were to look up from within a globular cluster, you'd see thousands of stars so close and bright that it might feel like daylight. In contrast, our own galactic neighborhood feels almost empty by comparison. Here in the Milky Way, stars are spread out, with vast stretches of dark space between them. But in a globular cluster, the sheer density of stars creates an environment that's both breathtaking and chaotic. Imagine trying to navigate through a sky where stars are so close that their gravitational pull constantly tugs at one another, creating a dynamic and ever-changing stellar dance. This incredible density isn't just a visual spectacle, it's also a key factor in how globular clusters evolve. With stars so close together, interactions are frequent. Stars can collide, merge, or even be flung out of the cluster entirely. It's a cosmic game of bumper cars where the rules are written by gravity. And yet, despite this chaos, globular clusters remain remarkably stable, holding together for billions of years. It's a testament to the incredible gravitational forces at play, binding these stars into a tight-knit community that defies the vast emptiness of space. So, while our night sky might feel serene and spacious, the view from inside a globular cluster would be a dazzling reminder of just how crowded and dynamic the universe can be. It's a stark contrast that highlights the incredible diversity of cosmic environments and leaves us marveling at the sheer scale and complexity of the universe. Now, let's turn our attention to one of the most intriguing mysteries surrounding globular clusters, the curious case of the missing intermediate mass black holes. These elusive objects, which are thought to weigh anywhere from a few hundred to several thousand times the mass of our Sun, should, in theory, be lurking at the heart of these dense star systems. Yet, despite decades of searching, astronomers have come up almost empty-handed. So, where are they? Intermediate mass black holes occupy a fascinating middle ground between the smaller stellar mass black holes, formed from collapsing stars, and the supermassive black holes that dominate the centers of galaxies. Their existence is crucial for understanding how black holes grow and evolve over time. Globular clusters, with their dense stellar populations, seem like the perfect breeding grounds for these intermediate mass black holes. The frequent gravitational interactions and stellar collisions within these clusters should, in theory, create the ideal conditions for such black holes to form and thrive. But the evidence just isn't there. This absence raises some big questions. Are intermediate mass black holes simply harder to detect than we thought? Or do they not form in globular clusters at all? One possibility is that these black holes are ejected from their clusters during violent gravitational encounters. Imagine a cosmic game of tug-of-war, where the intense gravitational forces between stars and black holes could fling an intermediate mass black hole out into intergalactic space, leaving no trace behind. Another theory suggests that these black holes might merge with others, growing into supermassive black holes over time, which could explain why we don't see them in their intermediate stage. The implications of this mystery go far beyond globular clusters. If intermediate mass black holes are truly absent, it could challenge our understanding of how black holes form and evolve across the universe. It might even force us to rethink the processes that lead to the creation of supermassive black holes, which are thought to grow from smaller seeds over billions of years. Without these intermediate steps, the story of black hole evolution becomes far more complicated and far more fascinating. So, while the search for intermediate mass black holes continues, their absence remains one of the most puzzling enigmas in astrophysics. It's a reminder that even in the crowded, chaotic environments of globular clusters, the universe still holds secrets that defy our expectations, and as we keep searching, each discovery, or lack thereof, brings us closer to unraveling the mysteries of these cosmic giants. Now, shifting our gaze to another cosmic oddity, let's explore the fascinating phenomenon of blue stragglers. These stars stand out like rebellious teenagers in a crowd of elders, appearing younger, hotter, and more vibrant than their neighboring stars in globular clusters. But here's the twist: they shouldn't exist, at least not according to our understanding of stellar evolution. So, what's going on? Blue stragglers are stars that seem to defy the natural aging process. In a globular cluster where most stars are ancient and have long since exhausted their fuel, these stars shine with a youthful blue hue, burning hotter and brighter than their peers. This contradiction has puzzled astronomers for decades. How can stars in such an old environment appear so young? The answer lies in their unusual origins. One leading theory suggests that blue stragglers are the result of stellar collisions. In the densely packed environment of a globular cluster, stars often come dangerously close to one another. When two stars collide, their combined mass can create a new, more massive star that burns hotter and brighter than either of its predecessors. This rejuvenated star then takes on the appearance of a younger star, even though it's technically older than it looks. Another possibility is that blue stragglers form through binary star mergers. In this scenario, two stars in a close orbit around each other gradually spiral inward, eventually merging into a single, more massive star. This process can also produce a star that appears younger and hotter than its surroundings. The merger not only increases the star's mass but also stirs up its internal structure, reigniting nuclear fusion and giving it a second lease on life. The existence of blue stragglers challenges our understanding of how stars evolve, especially in the crowded environments of globular clusters. They remind us that the universe is full of surprises, and even the most well-established theories can be upended by a single observation. By studying these enigmatic stars, astronomers hope to uncover new insights into the complex dynamics of stellar interactions and the life cycles of stars. So, while blue stragglers may seem like cosmic anomalies, they are actually key pieces of the puzzle in understanding the intricate dance of stars within globular clusters. Their defiance of stellar evolution not only captivates our curiosity but also pushes the boundaries of what we know about the universe. And as we continue to study them, we may find that they hold even more secrets waiting to be uncovered. Now, let's turn our attention to a mystery that has left astronomers scratching their heads: the puzzling absence of dark matter in globular clusters. Unlike galaxies, which are thought to be embedded in vast halos of dark matter, globular clusters seem to defy this cosmic norm. This discovery raises important questions about the role of dark matter in the universe and how these dense star systems formed in the first place. Dark matter is an invisible substance that makes up a significant portion of the universe's mass. It doesn't emit, absorb, or reflect light, making it detectable only through its gravitational effects. In galaxies, dark matter acts like an invisible scaffold, holding everything together and influencing the motion of stars and gas. But when scientists looked at globular clusters, they found something unexpected. These clusters appear to have little to no dark matter at all. This finding is surprising because, based on our current understanding, dark matter should play a crucial role in the formation and stability of cosmic structures. So, why do globular clusters seem to lack it? One possibility is that globular clusters formed in regions where dark matter was less concentrated. Unlike galaxies, which grew by accumulating dark matter over billions of years, globular clusters may have originated in areas where ordinary matter dominated. This could explain why they are so densely packed with stars but lack the dark matter halos we see in larger structures. Another theory suggests that dark matter might have been present in globular clusters initially but was stripped away over time. As these clusters orbit their host galaxies, they could have been subjected to intense gravitational forces that pulled away their dark matter, leaving behind only the visible stars we observe today. This process, known as tidal stripping, might explain why globular clusters now appear to be devoid of dark matter. The absence of dark matter in globular clusters challenges our understanding of how these structures form and evolve. It also raises questions about the nature of dark matter itself. If dark matter is as pervasive as we believe, why doesn't it show up in globular clusters? Could there be different types of dark matter, some of which don't interact with globular clusters in the same way? Or is there something fundamentally different about how these clusters came into existence? This enigma not only deepens the mystery of dark matter, but also highlights the unique nature of globular clusters. They are cosmic outliers, defying expectations and forcing us to rethink our assumptions about the universe. As astronomers continue to study these clusters, they hope to uncover clues that could shed light on the true nature of dark matter and its role in shaping the cosmos. So, while globular clusters may lack dark matter, they are far from lacking in intrigue. Their peculiar properties remind us that the universe is full of surprises, and every discovery brings us closer to understanding the grand tapestry of the cosmos. And as we delve deeper into this mystery, we may find that the answers lie not just in what we see, but in what remains hidden in the shadows of the universe. Now, let's shift our focus to another fascinating discovery: rogue planets lurking within globular clusters. These mysterious worlds, unbound to any star, drift freely through the dense stellar neighborhoods of these ancient clusters. Unlike the planets in our solar system, which orbit a central star, rogue planets are cosmic nomads wandering through space without a gravitational anchor. Their existence raises intriguing questions about how planets form and survive in such extreme environments. Rogue planets are thought to form in one of two ways. The first possibility is that they were born like any other planet, forming from the swirling disks of gas and dust around young stars. However, violent gravitational interactions within the densely packed globular cluster could have ejected them from their original systems, sending them hurtling into the void. Imagine a cosmic game of pinball where planets are flung out of their orbits by the gravitational pull of passing stars. This chaotic environment makes globular clusters a likely place to find these wandering worlds. The second theory suggests that some rogue planets might have formed on their own, directly from collapsing clouds of gas and dust, without ever being part of a star system. This process, known as gravitational collapse, could occur in the dense cores of globular clusters, where the sheer abundance of material might allow planets to form independently. These solitary worlds would then roam freely, untethered to any star. The discovery of rogue planets in globular clusters provides valuable insights into the dynamics of planetary systems in dense stellar environments. It challenges our understanding of how planets form and survive, especially in regions where gravitational interactions are frequent and intense. For instance, the presence of these free-floating planets suggests that planetary systems in globular clusters might be less stable than those in quieter regions of space, like our own galactic neighborhood. Moreover, rogue planets could serve as cosmic time capsules, preserving clues about the conditions in which they formed. By studying their composition and trajectories, astronomers can piece together the history of their parent clusters and the processes that shaped them. These wandering worlds might even hold secrets about the early universe, offering a glimpse into the chaotic environments where the first stars and planets were born. The existence of rogue planets in globular clusters also raises fascinating possibilities for the future of space exploration. Could these free-floating worlds harbor life, even without the warmth of a nearby star? Some scientists speculate that rogue planets might have subsurface oceans, kept liquid by internal heat or radioactive decay, creating potential habitats for life in the most unexpected places. As we continue to explore the mysteries of globular clusters, rogue planets remind us that the universe is full of surprises. These wandering worlds challenge our assumptions and open up new avenues for discovery. They show us that even in the most crowded corners of the cosmos, there are still uncharted territories waiting to be explored. And as we uncover more about these enigmatic planets, we may find that they hold the key to understanding not just globular clusters, but the very nature of planetary systems across the universe. Now, let's turn our attention to a puzzling feature of globular clusters: their surprising lack of gas and dust. Unlike many other regions of the universe, these ancient star clusters seem to have run out of the raw materials needed to create new stars. This absence of gas and dust is particularly curious because globular clusters are among the oldest structures in the cosmos, with some dating back nearly as far as the Big Bang. So, where did all the gas go, and why can't these clusters form new stars? One leading theory suggests that globular clusters lost their gas early in their lifetimes. During their formation, intense bursts of star formation may have used up much of the available gas and dust. Additionally, the radiation and stellar winds from these newly formed stars could have blown the remaining gas out of the cluster entirely. Imagine a cosmic wind sweeping through the cluster, clearing away the material needed to birth new stars. Over billions of years, this process would leave globular clusters gas-poor and unable to sustain further star formation. Another possibility is that globular clusters were stripped of their gas by external forces. As these clusters orbit their host galaxies, they pass through regions filled with hot, diffuse gas. The pressure from this intergalactic medium could have gradually stripped away the gas within the clusters, leaving them barren. It's like a ship sailing through a storm, losing its cargo to the relentless waves. Over time, this process would deplete the clusters of their star-forming materials, effectively halting the creation of new stars. The lack of gas and dust has profound implications for the evolution of globular clusters. Without the ability to form new stars, these clusters are essentially frozen in time, preserving a snapshot of the early universe. Their stars age and evolve, but no new generations of stars are born to replace them. This makes globular clusters invaluable to astronomers, as they provide a window into the conditions and processes that shaped the universe in its infancy. However, the absence of gas also means that globular clusters are no longer active stellar nurseries. Unlike younger star clusters or galaxies which continue to form stars, globular clusters are relics of a bygone era. Their inability to produce new stars limits their ability to evolve dynamically, making them more static compared to other cosmic structures. This lack of ongoing star formation also means that globular clusters are dominated by older, cooler stars, giving them their characteristic reddish hue. Despite their gas-poor state, globular clusters remain fascinating objects of study. Their unique conditions challenge our understanding of how star formation works in different environments. They also raise questions about the fate of other star clusters and galaxies over cosmic timescales. Could all star-forming regions eventually run out of gas, or do some retain the ability to create new stars indefinitely? By studying globular clusters, astronomers hope to uncover clues about the life cycles of stellar systems across the universe. As we continue to explore these ancient clusters, the mystery of their missing gas reminds us that the universe is full of surprises. It challenges us to rethink our assumptions about how stars and galaxies evolve, and it highlights the complex interplay of forces that shape the cosmos. Globular clusters may no longer be able to form new stars, but they continue to illuminate the past, offering us a glimpse into the early days of the universe and the processes that shaped it. Now, let's dive into another fascinating mystery of globular clusters' multiple stellar populations. At first glance, you might assume that all the stars in a globular cluster are identical, born from the same cloud of gas and dust at the same time. But here's where things get intriguing. Astronomers have discovered that many globular clusters contain stars with strikingly different chemical compositions. This discovery has turned our understanding of these clusters upside down, revealing a far more complex history than we ever imagined. So, how can stars in the same cluster have different chemical fingerprints? One leading theory suggests that globular clusters experienced multiple waves of star formation. Imagine the first generation of stars forming from the pristine gas of the early universe. These stars would have been rich in hydrogen and helium with very few heavier elements. But as these stars aged and eventually exploded as supernova, they enriched the surrounding gas with heavier elements like oxygen, carbon, and iron. This enriched gas then collapsed to form a second generation of stars, which would naturally have a different chemical makeup than their predecessors. But the story doesn't end there. Some globular clusters show evidence of not just two, but three or even more distinct populations of stars. This raises the question, how did these clusters manage to retain enough gas to form multiple generations of stars, especially given their lack of gas today? One possibility is that globular clusters were once much more massive, with enough gas to sustain several rounds of star formation before losing it to stellar winds or interactions with their host galaxies. Another idea is that globular clusters may have captured gas from their surroundings, allowing them to form new stars even after their initial gas supply was depleted. The discovery of multiple stellar populations has profound implications for our understanding of globular clusters. It suggests that these clusters are not the simple, single-generation systems we once thought they were. Instead, they are dynamic environments that have undergone complex processes of star formation and chemical enrichment over billions of years. This complexity makes globular clusters even more valuable as cosmic laboratories, offering insights into how stars and galaxies evolve over time. Interestingly, the presence of multiple populations also challenges our understanding of stellar evolution. Stars with different chemical compositions age differently, meaning that a single globular cluster can contain stars at various stages of their life cycles. This diversity adds another layer of intrigue to these ancient clusters, as astronomers work to unravel the intricate relationships between their stars and the processes that shape them. As we continue to study globular clusters, the mystery of their multiple stellar populations reminds us that the universe is far more complex than it appears. These clusters are not just relics of the past, they are dynamic systems that have evolved in surprising ways over cosmic time. By unraveling their secrets, we gain a deeper understanding of the forces that shape the cosmos and the intricate dance of stars, gas, and time that has brought us to where we are today. Now, let's shift our gaze to one of the most thrilling phenomena in globular clusters: hypervelocity stars. These are stars that have been flung out of their clusters at mind-boggling speeds, some traveling so fast they could escape the gravitational pull of their host galaxy entirely. Imagine a star racing through space at millions of miles per hour, leaving its home cluster far behind. It's a cosmic spectacle that challenges our understanding of how stars move and interact. So, how do these stars reach such incredible speeds? The leading theory points to gravitational interactions within globular clusters. Picture this: a star gets too close to a massive black hole lurking at the cluster's center. The black hole's immense gravity acts like a slingshot, flinging the star outward at an astonishing velocity. In some cases, the star might even be part of a binary system, two stars orbiting each other. If one star gets captured by the black hole, the other can be ejected at hypervelocity, like a cosmic game of gravitational pinball. But black holes aren't the only culprits. Sometimes, close encounters between stars in these densely packed clusters can also result in hypervelocity ejections. When two stars pass near each other, their gravitational interaction can transfer enough energy to send one of them hurtling away at breakneck speeds. It's a chaotic dance of gravity where even a slight nudge can send a star on a one-way journey across the galaxy. What makes hypervelocity stars so fascinating is not just their speed, but what they tell us about the environments that created them. By studying these stars, astronomers can learn more about the dynamics of globular clusters and the role of black holes in shaping their evolution. Each hypervelocity star is like a cosmic messenger, carrying clues about the forces that govern these ancient star systems. Interestingly, some of these stars are so fast that they might eventually leave their galaxies entirely, becoming intergalactic wanderers. Imagine a star traveling through the vast emptiness between galaxies, a lone traveler in the cosmic void. It's a reminder of just how dynamic and unpredictable the universe can be, even in the seemingly stable environment of a globular cluster. As we continue to uncover the secrets of hypervelocity stars, we're reminded that globular clusters are not just static relics of the past. They are dynamic, ever-changing systems where stars are born, live, and sometimes are flung into the unknown at incredible speeds. These high-speed stars are a testament to the power of gravity and the complex interactions that shape the cosmos, offering us a glimpse into the forces that drive the universe's endless dance. Now, let's turn our attention to another fascinating phenomenon in globular clusters: stars that manage to break free entirely, embarking on a journey beyond their home clusters. These stellar escapees, often referred to as intergalactic wanderers, are stars that have been ejected from their globular clusters and are now drifting through the vast expanse of space, untethered to any galaxy. But how do stars achieve such a dramatic escape? The process often begins with the intense gravitational interactions within globular clusters. These clusters are densely packed with stars, and their close proximity means that stars frequently pass near one another. When two stars come close enough, their gravitational fields can interact in ways that dramatically alter their paths. In some cases, these interactions can transfer enough energy to one of the stars, propelling it outward at such high speeds that it escapes the cluster's gravitational pull entirely. It's like a cosmic game of billiards where a single collision or near miss can send a star hurtling into the void. Another mechanism involves the presence of massive objects within the cluster, such as black holes or binary star systems. When a star passes too close to a black hole, the immense gravitational force can slingshot the star outward, much like the hypervelocity stars we discussed earlier. Similarly, in a binary star system, if one star is captured or disrupted by a massive object, the other can be ejected at high speeds, sometimes fast enough to leave the cluster altogether. These events are rare but powerful, showcasing the chaotic and dynamic nature of globular clusters. Interestingly, some of these escaping stars don't just leave their clusters, they leave their host galaxies as well. Once free from the cluster's gravity, these stars can travel through intergalactic space, becoming true wanderers of the cosmos. Imagine a star drifting alone through the darkness between galaxies, a solitary traveler in an otherwise empty expanse. These intergalactic stars are a testament to the incredible forces at play in the universe, where even the most stable-looking systems can give rise to extraordinary events. What makes these stellar escapes so intriguing is what they reveal about the environments that produce them. By studying these runaway stars, astronomers can gain insights into the internal dynamics of globular clusters, such as the frequency of stellar interactions and the role of massive objects like black holes. Each escaping star carries with it a story of the forces that shaped its journey, offering clues about the complex interplay of gravity and motion in these ancient star systems. As we explore the mysteries of these intergalactic wanderers, we're reminded once again that globular clusters are far from static. They are dynamic, ever-changing systems where stars are constantly on the move, sometimes even breaking free to explore the universe beyond. These stellar escapes are a vivid reminder of the power of gravity and the unpredictable nature of the cosmos, where even the stars themselves can become adventurers in the vastness of space. Now, shifting our focus to another cosmic mystery, let's delve into the puzzling absence of neutron stars within globular clusters. Neutron stars, the incredibly dense remnants left behind after a supernova explosion, are a common sight in many parts of the universe. Yet within globular clusters, they seem to be conspicuously missing. This raises the question, why are these stellar remnants so rare in these ancient star systems? One leading theory suggests that neutron stars might be ejected from globular clusters during their formation. When a massive star explodes as a supernova, the resulting neutron star can receive a powerful kick from the explosion. This kick, caused by asymmetries in the supernova process, can propel the neutron star at speeds high enough to escape the cluster's gravitational pull. Imagine a cosmic cannonball being launched into space, leaving its birthplace behind. This ejection mechanism could explain why so few neutron stars remain within globular clusters, despite the fact that these clusters are home to countless stars that have reached the end of their lives. Another possibility is that neutron stars in globular clusters are simply harder to detect. Neutron stars are incredibly small, often only about 12 miles across, and they emit most of their radiation in the form of X-rays or radio waves. If a neutron star isn't actively accreting material or emitting pulses, it can easily go unnoticed. In the crowded environment of a globular cluster, where stars are packed tightly together, spotting a faint, quiet neutron star becomes an even greater challenge. It's like trying to find a needle in a cosmic haystack. There's also the intriguing idea that some neutron stars might merge with other stars or black holes within the cluster, effectively disappearing from view. In such dense environments, close encounters between stars are common, and a neutron star could be captured by a binary system or even collide with another neutron star, leading to the formation of a black hole. These mergers would not only remove the neutron star from the cluster, but also leave behind little trace of its existence. The mystery of the missing neutron stars in globular clusters highlights the complex and dynamic nature of these ancient star systems. While we have some plausible explanations, the full story remains elusive. Each missing neutron star represents a piece of the puzzle, urging astronomers to refine their observations and theories. As we continue to study these clusters, we may uncover new clues that shed light on the fate of these enigmatic stellar remnants. This puzzle also reminds us that globular clusters, despite their age and apparent stability, are far from static. They are dynamic environments where stars are born, die, and sometimes vanish without a trace. The absence of neutron stars is just one more layer of intrigue in the ongoing story of these cosmic time capsules, challenging us to rethink what we know about the life cycles of stars and the forces that shape their destinies. Now, let's turn our attention to a discovery that connects globular clusters to the very fabric of the cosmos itself. These ancient star systems may have played a pivotal role in the formation and evolution of galaxies, acting as cosmic building blocks in the early universe. Picture this: billions of years ago, when the universe was young and galaxies were just beginning to take shape, globular clusters could have been among the first structures to form. Their dense, tightly bound groups of stars might have served as the seeds around which galaxies grew, providing the gravitational scaffolding needed to pull together gas, dust, and other stars into larger, more complex systems. One compelling idea is that globular clusters were the original proto-galaxies, small, dense collections of stars that merged and interacted over time to create the sprawling galaxies we see today. In this scenario, globular clusters would have acted like cosmic Lego bricks, combining and clustering together to form the foundations of galaxies like our own Milky Way. This theory is supported by the fact that many globular clusters are incredibly old, dating back to a time when the universe was still in its infancy. Their age and composition make them perfect candidates for these early building blocks, but the role of globular clusters doesn't stop there. As galaxies evolved, these clusters continued to influence their development. For example, globular clusters orbiting a galaxy can contribute to its overall structure and dynamics. Their gravitational pull can help shape the distribution of stars and gas within the galaxy, and their movements can even trigger waves of star formation. In some cases, globular clusters may have been absorbed into their host galaxies, their stars becoming part of the galactic halo or disk. This process would have enriched the galaxy with older, metal-poor stars, adding to its diversity and complexity. Interestingly, globular clusters also provide clues about the violent history of galaxy formation. Many galaxies, including the Milky Way, show evidence of past collisions and mergers with smaller galaxies. During these cosmic encounters, globular clusters could have been stripped from their original host galaxies and captured by larger ones. This would explain why some galaxies have globular clusters with different ages and chemical compositions. They are essentially cosmic refugees carrying the history of their former homes. The idea that globular clusters played a key role in galactic evolution challenges us to rethink how galaxies came to be. These ancient star systems, once thought of as mere relics of the past, may have been active participants in shaping the universe as we know it. By studying them, we gain insights into the processes that transformed a chaotic, early universe into the structured, star-filled cosmos we see today. As we continue to explore the mysteries of globular clusters, we uncover not just their secrets, but also the story of how galaxies and perhaps even life itself came to exist. Now, let's shift our focus to one of the most intriguing questions surrounding globular clusters. Where did they come from? The origins of these ancient star systems remain a hotly debated topic in astronomy, with scientists proposing several competing theories to explain how they formed. One leading idea suggests that globular clusters were born within dwarf galaxies, small, faint galaxies that orbit larger ones like the Milky Way. In this scenario, globular clusters would have formed in the dense, star-rich environments of these dwarf galaxies before being stripped away during galactic interactions. This could explain why some globular clusters have chemical compositions similar to those found in dwarf galaxies, offering a tantalizing clue to their origins. Another compelling theory points to galactic collisions as the birthplace of globular clusters. When two galaxies collide, the immense gravitational forces and shock waves can trigger bursts of star formation, potentially giving rise to dense clusters of stars. These newly formed clusters could then evolve into the globular clusters we observe today. This idea is supported by the fact that some globular clusters appear to have formed more recently than others, suggesting that their creation might be tied to specific cosmic events such as galaxy mergers. However, not all globular clusters fit neatly into these explanations. Some appear to be far older than the galaxies they orbit, raising questions about whether they formed independently in the early universe. Could globular clusters have been among the first structures to emerge after the Big Bang, forming in the chaotic, gas-rich environment of the young cosmos? This possibility challenges our understanding of how structures in the universe came to be, suggesting that globular clusters might have a more complex and varied origin story than we once thought. Adding to the mystery, some globular clusters show evidence of multiple stellar populations, stars with different ages and chemical compositions within the same cluster. This phenomenon is difficult to explain if globular clusters formed in a single, rapid burst of star formation. Instead, it hints at a more prolonged and dynamic formation process, possibly involving multiple generations of stars or interactions with their surroundings. These findings have led astronomers to reconsider the traditional view of globular clusters as simple, ancient relics, instead seeing them as dynamic systems with a rich and varied history. As we continue to study these enigmatic star systems, the mystery of their origins only deepens. Each new discovery brings us closer to understanding how globular clusters formed, but it also raises new questions about the early universe and the processes that shaped it. Whether they were born in dwarf galaxies, forged in galactic collisions, or emerged independently in the cosmos, globular clusters remain a fascinating puzzle, offering us a glimpse into the universe's earliest days. And as we unravel their secrets, we may find that they hold the key to understanding not just their own origins, but the origins of galaxies themselves. Now, let's turn our attention to another fascinating aspect of globular clusters, the strange chemistry of their stars. Unlike the stars in our own galaxy, which tend to follow predictable patterns in their chemical makeup, stars within globular clusters often defy expectations. One of the most puzzling discoveries is the unusual abundance of certain elements, particularly helium and nitrogen, in these stars. These elements appear in much higher concentrations than we would typically expect, raising questions about how and why this happens. To understand this phenomenon, we need to look at the life cycle of stars within globular clusters. These clusters are incredibly dense, with stars packed so closely together that interactions between them are common. When stars collide or exchange material, it can lead to dramatic changes in their chemical composition. For example, when a star pulls material from a neighboring star, it can accumulate elements like helium and nitrogen, which are produced in the cores of older stars. This process, known as stellar cannibalism, might explain why some stars in globular clusters have such unusual chemistry, but there's more to the story. Some stars in globular clusters show signs of having formed from material that was already enriched with these elements. This suggests that earlier generations of stars in the cluster produced and released helium and nitrogen into their surroundings, which then became part of the raw material for new stars. This idea of multiple stellar populations within a single cluster adds another layer of complexity to the mystery. It implies that globular clusters didn't form all at once, but instead went through several phases of star formation, each leaving its mark on the chemical makeup of the cluster. The presence of these unusual elements also has implications for how we understand stellar evolution. Stars with higher levels of helium, for instance, burn hotter and brighter than their counterparts with normal compositions. This can affect how long they live and how they end their lives, potentially altering the overall structure and evolution of the cluster. Similarly, the abundance of nitrogen can influence the way stars cool and expand, adding another twist to the already complex story of globular clusters. As we continue to study these chemically peculiar stars, we're not just learning about globular clusters, we're gaining insights into the broader processes that shape the universe. The strange chemistry of these stars challenges our assumptions and pushes us to rethink how stars form, evolve, and interact in dense environments. And as we uncover more about these cosmic anomalies, we're reminded that the universe is full of surprises waiting to be discovered. Next, we'll explore another curious feature of globular clusters, the surprising shortage of red giant stars in some of these ancient systems. Now, shifting our gaze to another intriguing mystery, let's delve into the curious case of missing red giants in globular clusters. Red giants, the luminous, aging stars that mark the final stages of a star's life, are a common sight in many stellar systems. Yet, in some globular clusters, these stars seem to be conspicuously absent. This shortage has puzzled astronomers, as red giants are typically expected to be abundant in these ancient star systems. So, what could be causing their absence? One theory suggests that the unique environment of globular clusters might play a role. These clusters are densely packed with stars, leading to frequent gravitational interactions. It's possible that some red giants are being ejected from the clusters entirely, flung out into the vastness of space by close encounters with other stars or even black holes. This process, known as dynamical ejection, could explain why we see fewer red giants than expected. Another possibility is that the intense gravitational forces within the cluster might disrupt the normal evolution of stars, preventing them from reaching the red giant phase altogether. Another angle to consider is the difficulty of detecting red giants in these environments. Globular clusters are so densely populated that distinguishing individual stars can be a challenge, especially when they're located near the cluster's core. The bright light from other stars might overshadow the red giants, making them harder to spot. Additionally, some red giants might be obscured by dust or other interstellar material within the cluster, further complicating their detection. There's also the intriguing idea that the stars in these clusters might be evolving differently than we expect. For instance, the unusual chemical compositions we discussed earlier could influence how stars age, potentially causing them to skip the red giant phase entirely or transition through it more quickly. This would mean that red giants are not missing, they're just not forming in the way we're used to seeing in other parts of the universe. The mystery of the missing red giants is a reminder of how much we still have to learn about globular clusters. These ancient systems continue to challenge our understanding of stellar evolution and the forces that shape the cosmos. As we piece together the clues, we're not just solving a puzzle about red giants, we're uncovering deeper truths about how stars live, die, and interact in some of the most extreme environments in the universe. Next, we'll explore another fascinating aspect of globular clusters, the role of binary stars and how their interactions shape the dynamics of these dense stellar systems. Now, let's turn our attention to another fascinating feature of globular clusters, the role of binary stars. Binary star systems, where two stars orbit a common center of gravity, are incredibly common in these dense stellar environments. In fact, studies suggest that a significant portion of stars in globular clusters are part of binary or even multiple star systems. This prevalence isn't just a curiosity, it has profound implications for how these clusters behave and evolve over time. The interactions between binary stars can dramatically influence the dynamics of a globular cluster. For instance, when two stars in a binary system come close to another star or a black hole, the gravitational forces at play can lead to some extraordinary outcomes. One star might be ejected from the cluster entirely, while the other could be flung into a tighter orbit or even merge with its companion. These interactions can also transfer energy between stars, altering the overall structure of the cluster and contributing to its gradual expansion or contraction. Binary stars also play a key role in the formation of exotic objects like blue stragglers, which we discussed earlier. When two stars in a binary system merge, they can create a single, more massive star that appears younger and hotter than its neighbors. This process not only explains the presence of blue stragglers, but also highlights how binary interactions can defy our expectations of stellar evolution. Another intriguing aspect is how binary stars can act as cosmic energy sinks. In densely packed globular clusters, stars are constantly interacting, and these encounters can heat up the cluster, causing it to expand. However, binary systems can absorb some of this energy, helping to stabilize the cluster and slow down its expansion. This delicate balance between heating and cooling is crucial for understanding the long-term evolution of globular clusters. The study of binary stars in globular clusters also provides valuable insights into the formation of compact objects like neutron stars and black holes. When a binary system includes a massive star, its eventual collapse into a neutron star or black hole can lead to dramatic events such as X-ray bursts or even gravitational wave emissions. These phenomena not only shed light on the life cycles of stars, but also offer clues about the history and composition of the clusters themselves. The prevalence of binary stars in globular clusters is a testament to the complexity and dynamism of these ancient systems. Their interactions shape the clusters in ways we're only beginning to understand, offering a window into the intricate dance of gravity, energy, and stellar evolution. As we continue to explore these systems, we uncover not just the secrets of binary stars, but also the broader story of how galaxies and the universe itself have evolved over billions of years. Next, we'll dive into another mystery: why supernovae are so rarely observed in globular clusters despite their dense stellar populations. Now, shifting our gaze to another cosmic puzzle, let's explore why supernovae, those spectacular explosions marking the death of massive stars, are so rarely observed in globular clusters. Given the sheer density of stars in these clusters, one might expect supernovae to be a common sight. Yet they remain elusive, and this mystery has left astronomers scratching their heads for decades. One leading explanation lies in the nature of the stars themselves. Globular clusters are home to some of the oldest stars in the universe, and these stars tend to be low in mass. Supernovae, however, are the dramatic final acts of massive stars, those at least 8 times heavier than our Sun. These massive stars burn through their fuel quickly, living fast and dying young in a brilliant explosion. But in globular clusters, such massive stars are rare. Most of the stars here are smaller, cooler, and far more long-lived, meaning they end their lives quietly as white dwarfs rather than in fiery supernovae. Another factor could be the unique environment of globular clusters. The dense packing of stars means that gravitational interactions are frequent and intense. It's possible that massive stars, which are more susceptible to these interactions, are either ejected from the cluster before they can explode or merge with other stars, altering their fate. For instance, if two smaller stars collide and merge, they might form a more massive star, but even then, the conditions might not always lead to a supernova. Instead, the merged star could evolve into a blue straggler or another exotic object. bypassing the supernova stage entirely. There's also the possibility that supernovae do occur in globular clusters, but they're simply harder to detect. The dense stellar environment could obscure the light from these explosions, making them less visible to our telescopes. Additionally, the remnants of supernova, such as neutron stars or black holes, might be ejected from the cluster due to the powerful gravitational kicks they receive during the explosion, leaving little trace behind. This scarcity of supernova in globular clusters challenges our understanding of stellar evolution and the life cycles of stars in dense environments. It also raises questions about how these clusters have evolved over billions of years. Without the frequent injection of energy and heavy elements from supernova, globular clusters might have followed a very different evolutionary path compared to galaxies, where supernova play a crucial role in shaping their structure and chemistry. As we continue to study these ancient star systems, the mystery of the missing supernova serves as a reminder of how much we still have to learn about the universe. Next, we'll turn our attention to another curious feature of globular clusters: their strange and often unexpected orbits around their host galaxies. Now, let's venture into the peculiar world of globular cluster orbits, where the rules of motion seem to defy expectations. While most objects in a galaxy, like stars and planets, follow predictable paths in sync with their host galaxy's rotation, globular clusters often march to the beat of their own cosmic drum. Some of these ancient star systems orbit their galaxies in ways that leave astronomers both fascinated and puzzled. Imagine a galaxy spinning like a giant pinwheel, with stars and gas swirling in a graceful, coordinated dance. Now picture a globular cluster moving in the opposite direction, cutting against the flow like a rebellious swimmer in a river. These retrograde orbits, as they're called, are one of the strangest features of globular clusters. Why would these clusters move backward against the natural rotation of their galaxy? The answer lies in their origins. Many globular clusters are thought to have formed independently, possibly in smaller galaxies that were later absorbed by larger ones. When these smaller galaxies were captured, their globular clusters were dragged along, often retaining their original orbits, which could be completely out of sync with the new host galaxy's rotation. But retrograde orbits aren't the only oddity. Some globular clusters follow highly elliptical or tilted paths, looping far above or below the galactic plane. These unusual trajectories suggest that these clusters have had dramatic encounters in the past, perhaps with other clusters or massive objects like black holes which altered their paths. Over time, these gravitational interactions can stretch and twist their orbits into the strange shapes we observe today. What's even more intriguing is how these orbits impact the clusters themselves. Moving against the flow or on a tilted path exposes globular clusters to stronger tidal forces from their host galaxy. These forces can strip away stars, gradually eroding the cluster over billions of years. Yet, despite this, many globular clusters have survived. Their strange orbits are testament to their resilience and the dynamic history of the universe. The study of these orbits not only sheds light on the life stories of globular clusters, but also provides clues about the formation and evolution of galaxies themselves. By tracing the paths of these ancient star systems, astronomers can piece together the history of galactic collisions, mergers, and the cosmic dance that has shaped the universe as we know it. As we unravel the mysteries of these strange orbits, we're reminded once again that globular clusters are more than just dense collections of stars. They're cosmic storytellers, preserving the secrets of the universe's past. Next, we'll explore how tidal forces from their host galaxies continue to shape the fate of these enigmatic star systems. Now, let's dive into the powerful influence of tidal forces and how they shape the destiny of globular clusters. These ancient star systems, though densely packed and seemingly resilient, are not immune to the relentless pull of their host galaxies. Tidal forces, the gravitational tug of war between a galaxy and its globular clusters, play a crucial role in determining the lifespan and structure of these cosmic gatherings. Picture a globular cluster orbiting its host galaxy. As it moves, the side of the cluster closest to the galaxy feels a stronger gravitational pull than the side farther away. This difference in force stretches the cluster, much like the way the moon's gravity creates tides on Earth. Over time, this stretching can pull stars away from the cluster's outer edges, scattering them into the surrounding galaxy. This process, known as tidal stripping, gradually erodes the cluster, leaving it smaller and less dense. But tidal forces don't just act in isolation. The shape and path of a globular cluster's orbit can amplify their effects. Clusters that pass close to the galactic center or through dense regions of the galaxy experience stronger tidal forces, accelerating the loss of stars. Even clusters on highly elliptical orbits, which swing far out and then plunge back toward the galaxy, are vulnerable. Each close encounter with the galaxy's core can strip away more stars, slowly chipping away at the cluster's structure. Interestingly, this process isn't just destructive, it also contributes to the galaxy's evolution. The stars stripped from globular clusters become part of the galaxy's halo, a diffuse cloud of stars surrounding the main disk. In this way, globular clusters act as cosmic nurseries, seeding their host galaxies with stars over billions of years. Yet, as they lose stars, the clusters themselves grow fainter and less distinct, eventually dissolving into the galactic background. The role of tidal forces also raises questions about the ultimate fate of globular clusters. While some may survive for billions of years, others, especially those on chaotic or close orbits, could be completely torn apart. This gradual dissolution is a reminder of the dynamic and ever-changing nature of the universe, where even the most tightly bound systems are subject to the forces of time and gravity. As we explore the impact of tidal forces, we gain a deeper appreciation for the delicate balance that governs the lives of globular clusters. These star systems, though ancient and enduring, are not eternal. Their gradual erosion tells a story of cosmic forces at work, shaping the universe in ways both subtle and profound. Next, we'll uncover another mystery: why dwarf galaxies, often thought to be companions to globular clusters, are curiously absent in many cases. Now, shifting our gaze to another cosmic puzzle, let's explore the curious absence of dwarf galaxies around globular clusters. At first glance, you might expect these ancient star systems to have dwarf galaxy companions, given their similar ages and chemical compositions. Yet, the reality is far more mysterious. Despite their shared origins in the early universe, globular clusters and dwarf galaxies seem to exist in isolation from one another, leaving astronomers scratching their heads. Dwarf galaxies, as their name suggests, are smaller, fainter versions of regular galaxies, often containing billions of stars. They're thought to be some of the first structures to form in the universe, much like globular clusters. Given this shared history, it's natural to assume that globular clusters might be found orbiting or embedded within dwarf galaxies. However, observations tell a different story. While some globular clusters are associated with larger galaxies, very few are found in close proximity to dwarf galaxies. This raises the question: why are these two ancient cosmic structures so rarely seen together? One possible explanation lies in the chaotic environment of the early universe. During this time, galaxies and star clusters were forming in a turbulent sea of gas and dark matter. It's possible that globular clusters formed independently, separate from dwarf galaxies, in regions where conditions were just right for dense star systems to emerge. Alternatively, some globular clusters may have once been part of dwarf galaxies, but were stripped away during galactic collisions or interactions, leaving them orphaned in the vastness of space. Another intriguing theory suggests that dwarf galaxies and globular clusters might have formed under different conditions, even if they share similar ages. For example, globular clusters could have originated in regions with higher densities of gas, allowing them to form tightly bound star systems, while dwarf galaxies might have formed in areas with more diffuse material, leading to looser structures. This difference in formation environments could explain why the two rarely coexist. The mystery deepens when we consider the chemical similarities between globular clusters and dwarf galaxies. Both contain stars with low amounts of heavy elements, indicating they formed early in the universe's history. Yet, the lack of a clear connection between them challenges our understanding of how these structures evolved. Are globular clusters the remnants of disrupted dwarf galaxies, or did they form through entirely different processes? The answers remain elusive, but each discovery brings us closer to unraveling this cosmic enigma. As we ponder the missing link between globular clusters and dwarf galaxies, we're reminded of the complexity of the universe's early days. These ancient structures, though seemingly similar, may have followed vastly different paths to reach their current states. Next, we'll turn our attention to how globular clusters serve as cosmic time capsules, preserving clues about the universe's infancy and the formation of its first stars. Now, let's step into the role of cosmic archaeologists as we uncover how globular clusters act as time capsules, preserving secrets from the dawn of the universe. These ancient star systems are like celestial libraries, holding records of the conditions and processes that shaped the cosmos in its infancy. By studying them, astronomers can piece together the story of how the first stars and galaxies came to be. Globular clusters are unique in that they contain some of the oldest stars in the universe, many of which formed just a few 100 million years after the Big Bang. These stars are like fossils frozen in time, offering a snapshot of the chemical makeup of the early universe. Unlike younger stars, which are enriched with heavier elements forged in supernova, the stars in globular clusters are relatively pristine, containing mostly hydrogen and helium. This makes them invaluable for understanding the composition of the universe before heavier elements became widespread. One of the most fascinating aspects of globular clusters is their ability to preserve multiple generations of stars within the same system. While most of the stars in a cluster formed during its initial burst of star formation, some clusters show evidence of later generations of stars. These younger stars, though still ancient by human standards, provide clues about how star formation evolved over billions of years. By analyzing the chemical signatures of these stars, scientists can trace the history of star formation and the enrichment of the universe with heavier elements. Another key insight from globular clusters is their role in understanding the early stages of galaxy formation. Because they are so old and have remained relatively undisturbed, globular clusters offer a window into the conditions that existed when galaxies were first assembling. Their tightly bound structures suggest that they formed in regions of the universe where matter was densely packed, providing a glimpse into the chaotic environment of the early cosmos. This helps astronomers refine their models of how galaxies, including our own Milky Way, came to be. Perhaps most intriguing is the possibility that globular clusters could hold clues about the very first stars, known as population 3 stars. These stars, which have never been directly observed, are thought to have been massive and short-lived, seeding the universe with the first heavy elements. While no population 3 stars remain today, their chemical fingerprints might still be detectable in the oldest stars of globular clusters. Finding these traces could revolutionize our understanding of the universe's earliest moments. As we delve deeper into the mysteries of globular clusters, we're reminded of their profound significance in cosmic archaeology. They are not just relics of the past but active participants in the ongoing story of the universe. Next, we'll explore another fascinating aspect of these star systems: the strange alignment some globular clusters exhibit around their host galaxies, hinting at a deeper cosmic connection. Now, let's turn our attention to a peculiar phenomenon that has left astronomers both puzzled and intrigued: the strange alignments of globular clusters around their host galaxies. While these ancient star systems are known for their dense, spherical shapes, some of them seem to follow a pattern, almost as if they're arranged in a cosmic dance. This alignment isn't random. It hints at a deeper connection between globular clusters and the galaxies they orbit, one that might reveal secrets about the universe's structure and evolution. When astronomers first began mapping the positions of globular clusters, they noticed something unusual. Instead of being scattered randomly around their host galaxies, some clusters appeared to align along specific planes or axes. For example, in the case of the Milky Way, many of its globular clusters are concentrated in a particular direction, almost as if they're tracing an invisible path. This isn't just a coincidence. It suggests that these clusters might have formed or been influenced by the same processes that shaped the galaxy itself. One leading theory is that these alignments are remnants of the galaxy's formation. During the early stages of a galaxy's life, vast clouds of gas and dust collapsed under gravity, forming stars and star clusters. Some of these clusters may have been pulled into orbits that aligned with the galaxy's rotation or its overall structure. Over billions of years, these alignments have persisted, offering a glimpse into the chaotic conditions of the early universe. Another possibility is that these patterns are the result of interactions between galaxies. When galaxies collide or merge, their globular clusters can be redistributed, sometimes settling into new orbits that align with the merged galaxy's structure. This could explain why some galaxies, like the Andromeda Galaxy, show similar alignments in their globular cluster systems. These interactions might also explain why some clusters appear to move in retrograde orbits, traveling in the opposite direction to their galaxy's rotation. But why does this matter? These alignments aren't just curiosities. They could hold clues about the nature of dark matter. Some scientists believe that the distribution of globular clusters might reflect the underlying distribution of dark matter in a galaxy. If clusters align along specific planes, it could suggest that dark matter is arranged in a similar way, influencing the orbits of these star systems. This would provide a new way to study dark matter, one of the most elusive and mysterious components of the universe. As we continue to study these alignments, we're reminded of how interconnected the cosmos truly is. Globular clusters aren't just isolated relics. They're part of a larger cosmic web, shaped by the forces that govern the universe. Next, we'll explore another mystery tied to these ancient star systems: the surprising absence of planetary nebulae in globular clusters, despite the presence of aging stars that should produce them. What could this mean for our understanding of stellar evolution? Let's find out. Now, let's shift our focus to another intriguing puzzle surrounding globular clusters: the mysterious absence of planetary nebulae. These glowing shells of gas and dust, expelled by aging stars in their final stages of life, are a common sight in many parts of the universe. Yet, when it comes to globular clusters, they seem to be missing entirely. This is especially puzzling because globular clusters are home to countless aging stars that should, in theory, be producing these beautiful cosmic remnants. So, where are they? To understand why this is so strange, let's first look at what planetary nebulae are and how they form. When a star like our Sun reaches the end of its life, it swells into a red giant, shedding its outer layers into space. These layers form a glowing shell of gas and dust, illuminated by the intense ultraviolet radiation from the star's hot core. This is what we call a planetary nebula. They're some of the most visually stunning objects in the universe, often displaying intricate shapes and vibrant colors. Given that globular clusters are packed with old stars, many of which are in the red giant phase, we'd expect to see plenty of planetary nebulae within them. But we don't. One possible explanation for this absence lies in the unique environment of globular clusters. These clusters are incredibly dense, with stars packed closely together. This means that stars in globular clusters often interact with one another, either through close encounters or even collisions. These interactions could disrupt the formation of planetary nebulae. For example, if a red giant star loses its outer layers too quickly or unevenly due to gravitational tugs from nearby stars, the expelled material might not form the distinct shell we recognize as a planetary nebula. Instead, it could disperse into the surrounding space, becoming invisible to our telescopes. Another factor could be the low metallicity of stars in globular clusters. Metallicity refers to the abundance of elements heavier than hydrogen and helium in a star. Stars in globular clusters tend to have lower metallicity compared to stars in other parts of the galaxy. This could affect how they shed their outer layers and whether they form planetary nebulae. Some studies suggest that low metallicity stars might not produce the same bright, well-defined nebulae as their higher metallicity counterparts. Instead, their expelled material might be fainter or more diffuse, making it harder to detect. There's also the possibility that planetary nebulae in globular clusters simply don't last very long. The intense gravitational environment of a globular cluster could cause these delicate structures to dissipate quickly, leaving no trace behind. Alternatively, the radiation from nearby stars might ionize the gas in the nebulae, causing them to fade from view before we can observe them. The mystery of the missing planetary nebulae isn't just a curiosity. It has implications for our understanding of stellar evolution. If we can figure out why these nebulae are absent in globular clusters, it could shed light on how stars in dense environments evolve differently from those in more isolated regions. It might also help us refine our models of how planetary nebulae form and what conditions are necessary for their creation. As we ponder this cosmic riddle, we're reminded once again of how much we still have to learn about the universe. Globular clusters, with their ancient stars and unique environments, continue to challenge our assumptions and push the boundaries of our knowledge. Next, we'll explore how these dense star systems are playing a surprising role in the detection of gravitational waves, opening up new avenues for understanding the most violent events in the cosmos. Stay tuned. Now, let's turn our attention to a groundbreaking discovery that ties globular clusters to one of the most exciting fields in modern astronomy: gravitational wave detection. These ripples in space-time, first predicted by Albert Einstein over a century ago, are caused by some of the most violent events in the universe, such as the collisions of black holes or neutron stars. And it turns out, globular clusters might be the perfect cosmic laboratories for observing these elusive waves. The reason globular clusters are so well suited for this lies in their incredibly dense stellar populations. With hundreds of thousands of stars packed into a relatively small space, the chances of close encounters and collisions between stars are much higher than in other parts of the galaxy. This makes globular clusters hotspots for the formation of binary systems, pairs of stars that orbit each other. Over time, some of these binary systems can evolve into pairs of black holes or neutron stars, which are the primary sources of detectable gravitational waves. When two black holes or neutron stars spiral closer and closer together, they eventually merge in a cataclysmic event that sends ripples through spacetime. These ripples, or gravitational waves, can travel across the universe, carrying information about the objects that created them. Because globular clusters are so densely packed, the likelihood of such mergers occurring is significantly higher than in less crowded regions of space. This makes them ideal targets for gravitational wave observatories like LIGO and Virgo, which are designed to detect these faint signals from billions of light years away. But the story doesn't end there. The unique environment of globular clusters also affects the properties of the gravitational waves they produce. For example, the gravitational interactions between stars in a cluster can alter the orbits of binary systems, leading to mergers that might not happen in isolation. This means that the gravitational waves detected from globular clusters could have distinct signatures, providing astronomers with valuable clues about the dynamics of these dense stellar systems. Moreover, studying gravitational waves from globular clusters could help us answer some of the biggest questions in astrophysics. For instance, how do black holes and neutron stars form in such crowded environments? What role do globular clusters play in the overall population of these compact objects in the universe? And could these clusters be responsible for some of the mysterious gravitational wave signals we've already detected? As we continue to explore the cosmos, globular clusters are proving to be more than just ancient relics of the universe. They're active participants in some of the most dramatic events in space. By serving as natural detectors for gravitational waves, they're helping us unlock new secrets about the nature of black holes, neutron stars, and the fabric of space-time itself. And with each new discovery, we're reminded of how interconnected the universe truly is. Next, we'll take a look at the ultimate fate of these fascinating star systems and what their future holds in the ever-evolving cosmos. Stay with us as we uncover the final chapter in the story of globular clusters. As we peer into the distant future, the fate of globular clusters remains one of the most intriguing mysteries in astronomy. These ancient star systems, which have survived for billions of years, are not immune to the relentless forces of the universe. Over time, the very environment that makes them so fascinating, their dense stellar populations, could also lead to their eventual demise. One possible future for globular clusters is gradual dissolution. As they orbit their host galaxies, they are constantly subjected to tidal forces, gravitational tugs from the galaxy itself. Over billions of years, these forces can strip away stars from the outer regions of the cluster, slowly eroding its structure. Eventually, the cluster may lose so many stars that it can no longer hold itself together, dispersing its remaining members into the galactic halo. This process, known as tidal disruption, could turn these once tightly bound clusters into streams of stars, blending seamlessly into the broader galaxy. But dissolution isn't the only path. Some globular clusters may instead merge with their host galaxies. As they drift closer to the galactic center, the gravitational pull of the galaxy's core can draw them in. Over time, the cluster's stars could become part of the galaxy's bulge or even contribute to the formation of new structures like stellar disks. This merging process would effectively end the cluster's existence as a distinct entity, but its stars would live on, becoming part of the galaxy's larger stellar population. Interestingly, the fate of globular clusters may also depend on their interactions with other clusters or massive objects. Collisions between clusters, though rare, could lead to dramatic changes in their structure. Similarly, encounters with massive black holes or dense molecular clouds could accelerate their disruption. These interactions add another layer of complexity to the story, making the future of globular clusters as unpredictable as it is fascinating. Despite these challenges, some globular clusters may endure for trillions of years, outliving even their host galaxies. In a universe that continues to expand and evolve, these resilient star systems could become some of the last remnants of the early cosmos. Their survival would serve as a testament to the incredible forces that shaped them and the enduring legacy of the first stars. As we contemplate the future of globular clusters, we're reminded of the dynamic and ever-changing nature of the universe. These ancient star systems, which have witnessed the birth and death of countless stars, continue to hold secrets that challenge our understanding of space and time. Whether they dissolve, merge, or endure, their story is far from over, and their legacy will continue to inspire astronomers for generations to come. With that, we've reached the end of our journey through the strange and wondrous world of globular clusters. From their ancient origins to their mysterious futures, these cosmic relics have captivated our imaginations and deepened our understanding of the universe. If you've enjoyed this exploration, don't forget to like, subscribe, and hit the notification bell for more deep dives into the mysteries of space. Thanks for watching, and until next time, keep looking up. As we wrap up our journey through the 25 strange discoveries about globular clusters, it's clear that these ancient star systems are more than just relics of the early universe. They are cosmic enigmas that continue to challenge our understanding of space. From their densely packed stars to the puzzling absence of intermediate mass black holes, each discovery has revealed a new layer of mystery. We've explored how blue stragglers defy stellar evolution, how rogue planets wander freely, and how the lack of dark matter in these clusters raises questions about the very fabric of the cosmos. These findings remind us that globular clusters are not just beautiful to observe, they are also key to unlocking the secrets of the universe's past, present, and future. What makes globular clusters so fascinating is their ability to surprise us. Whether it's the hypervelocity stars racing through space, the strange chemistry of their stellar populations, or their unexpected orbits around galaxies, these clusters keep astronomers on their toes. They serve as cosmic time capsules, preserving clues about the formation of the first stars and the evolution of galaxies. Yet, for every answer they provide, they pose even more questions, ensuring that their study remains a vibrant and dynamic field of research. As we reflect on these discoveries, it's impossible not to feel a sense of awe. These clusters have witnessed the birth and death of countless stars, survived galactic collisions, and endured the relentless pull of tidal forces. They are a testament to the resilience and complexity of the universe, and their story is far from over. Whether they dissolve into streams of stars, merge with their host galaxies, or endure as some of the last remnants of the early cosmos, their legacy will continue to inspire curiosity and wonder. If you've enjoyed this deep dive into the mysteries of globular clusters, don't keep it to yourself. Share your thoughts in the comments below. What discovery surprised you the most? What questions do you still have about these cosmic wonders? And if you're hungry for more space mysteries, be sure to like, subscribe, and hit the notification bell so you never miss an update. Thanks for joining me on this journey through the stars, and until next time, keep exploring the wonders of the universe.